Welcome. In this recording, we're going to go over a common problem when loading large amount of data from a SQL database or a database of a sort and landing it into a data lake folder as Parquet. Now, the common problem is that of speed. So, for instance, you might have been through a scenario where you needed to copy a large table of, let's say, 100 gigs of data and land it into Parquet in an ADLS Gen2 data lake folder. Um, when you do this, sometimes your throughput is very, very slow, and you have no natural way of splitting or loading it in parallel due to the fact that you don't understand, either you don't have a delta or delta key, or don't have a partition key, or something that is useful in terms of loading. So, for instance, you want to load this 40 gig data set, and it takes you 40 minutes to load it and save it as Parquet in the data lake. Now, what we ultimately want to do is we want that to be a lot faster. So I'll show you the pipelines and how it works. So here's your traditional copy pipeline. So this is a very simple pipeline. I select everything from a table, a very large table or a wide table, and then I sync it into Parquet into a pipeline. So if we go and we look at the execution history of this pipeline, we can quickly see that it took roughly about 40 minutes. And if we look at some of the stats, so that is 37.7 million rows of data. And we can see that out of reading from source, and the sort of the actual copy duration is what took the longest, right? Now, this is obviously not ideal because we might be loading very, very large tables, and it just the throughput isn't good enough, right? So if we then think about how we could do this better, so we have another pipeline here called fast extractor. The fast extractor is a way of natural, well, this fast extractor pipeline, if we go and we look at the execution time, sorry, let's step back here, we can see that this one ran in 8 minutes. And what basically we did was we ran or we created shards or parallel executions. So we basically ran everything in parallel at the same time. And if we step into these, so remember we got about 8 megabytes on the previous one, but here we're getting 1.7 megabytes a second, so considerably slower per copy. However, we're running all of them in parallel, so the total execution is the sum. Well, is the longest execution of a pipeline, so the last one to complete. So how do we solve this? So obviously we need two things. The first thing is a way of enumerating or dynamically enumerating partitions. So if we let's step through the pipeline and have a look at it. So I set some execution parameters or variables. This happens to be some input variables that I grab as text concatenation for a select statement. The second thing I do is then I execute a bit of dynamic SQL to return the amount of partitions or sets that I want to process of my source table. So this has been set up to dynamically get the appropriate amount of partitions. and I'll walk through the SQL and how this works in a moment. And then a simple for each loop where I pass in um, another piece of dynamic SQL that then per item executes with specific where clauses in a table. So I get, and this one is set to run, sorry, with up to 32 parallel executions, right? So if we look at some of the SQL, and I should probably do is I should just do a trigger of this now. So I'm just going to go ahead. I have a table that I've been using. Let me switch that into focus. So I have this large wide table, and I'll show you what that looks like in a moment. I just want to kick off the the pipeline. So we go ahead, type in our schema name and our table name, and we hit OK, and we can gonna let that run in the background. So how this works. So if we look at the whole dynamic partition thing, if we step into Management Studio, so when we want to, well, if we look at this table, so I'm just going to go top, just going to select top 100 rows. And here we can see whilst I know that there is some IDs, we obviously want to build dynamic pipelines, so we don't want to care about yeah, how anything is constructed. So all I care about is getting some getting a way of partitioning this appropriately. So the first thing I want to do, or I have, is I have a parameter um, that I want to manage, or I've got a setting. So I want to make sure that each partition has a maximum of 1.6 million rows of data in them. And the reason we do this is because obviously in a data lake, if you want to ingest or ingest something using a copy into Synapse Analytics or use Polybase or any querying of Parquet files, you want to split these up appropriately, right? Um, and the reason you do this is because it's a lot faster to get the results back. And if you're doing ingestion in Synapse Analytics, after you store data in Park in a data lake, you then can use the polybase mechanism where you're not affecting your concurrency slots, and you're getting direct imp or execution from the compute nodes for the ingestion rather than going via control node into the compute nodes. So it's a lot faster to ingest the data. Right. So anyway, that's why I said I want to make sure that each partition that we build have roughly about 1.6 million rows of data. Okay, and first things first, I don't want to split up. So this one's configured to split up 30 partitions, but we'll get into that now. I just want to make sure that I understand how big this table is, how many rows, so I know how many partitions to build, right? So the first one is we're selecting out a count, or we're counting the amount of rows in the table, and we divide that by 1.6 million, and that gives us our partition count, right? And then what we do is we do a ceiling of this, so we round it up to the nearest whole number upwards, right? Or to the next whole number. So what we're going to do is I'm just going to select out the variable so that we can have a quick look at what this looks like when we execute it. So if we go ahead and run this, And I'm going to go copy this out. And I'm going to start a new query. Paste it in here, and let's start splitting it up. So, ooh, something went wrong. Did I not? Oh, sorry, my bad. I didn't see that. So first we have our partition count that we do, and then we have a seed table. So this is just, and please no one laugh. I just need to enumerate rows. And then we have a where clause. Right, cool. So first thing we do is we try to drop a temp table. That's just some housekeeping. And the second thing we do is we declare and set a variable. Okay, so if we look at the select statement, right, we are doing a count of our very large table, which is taking long to execute. There we go. And it's, so if we just go ahead and, oh no, if we go ahead and copy this out, so we just run an actual count on this table. I'm just going to go here. So just so we can show the amount of rows. So this table has got, oh, my connection is very slow. There we go. So this table's got 37 million rows. So when we ran the this partition query, I think we got a value of 24 partitions as a target. Yep, 24. So if we say, so if we go select the number we got divided by 24, we should get a number that's fairly close to 1.6 million, right? There we go. 1.57, yeah, so rounding error and some change, right? But at least we know each partition's got about 1.57, roughly about 1.6 million rows. Okay, cool. So that's the first thing we do. And then we take the result of that and we return it, we return the partition count out as a table, as a result set. So that looks like this, right? So we get a partition ID, so 0 to 23 for 24, and we get another the actual partition count, right? So we know how many partitions we're processing. Okay, so those are the first two things we get in our SQL. So if we just relate that back to the pipeline, so that is the first query we do. So that's our lookup. If we go into, let's just go into this guy whilst he's running. So we can now look at the get partitions output, and you can see here we're getting the partitions 0 to 24 or 0 to 23, right? Now those are passed forward into the for each loop. So let's go back into the pipeline. So in the for each loop, we then have in our source query, we have a bit of a dynamic SQL. So this is concatenation. So I'm just setting the variables, right? That I need. And let me show how that transact looks. Okay, so let's just step into SSMS again. So if we go back into the transact, so here we go. This looks like this. So I just showed you this part, the dynamic part, or the where I set the variables. So I pass in schema name, the table name, how many partitions, in our case it was 24, and then obviously it starts from 0 to 23, right? So this would have been the first execution. Then we're gonna go, I'm just gonna print, or actually I'll do select. Well, it doesn't matter. Let's do print. So anyway, what I then do is I go and um, I create a dynamic SQL call, and in this I also query the information schema columns. And the reason I do that is because I need to generate a row hash or some form of fairly unique key. So I'm making an assumption that the first three columns will give me some form of uniqueness. Now, this is hard coded, uh, but in a real life scenario, would probably work on a 10% of columns rounded up plus one. So if you have a four column wide, um, you know, table, you want to take the first two columns as your row ID. And the reason why this should be dynamic based on the table is because number one, let's say we don't know the key structure of the table, and also there's a law of diminishing returns on the effectiveness. So um, it will always be faster to load in parallel, but if you obviously don't want to stress your source system by running weird calculations and running filters on top of these, right? Because that can become very expensive from a SQL perspective. I find that it's fairly straightforward and effective in normal SQL Server. And Azure SQL DB, I don't have problems running these queries. But you know, anyway, you might want to rethink or think about the strategy in how you create these keys. Also, if there is no uniqueness in the first three columns in this case, then you will have a single partition. So that's just another thing to also think about. That it might, it won't fail. It will just become slow to load if if you can't generate unique hashes on the first three columns. And the hashes just needs to be unique enough so it does split up in appropriate partitions. Anyway, um, so if we then look at this dynamic SQL, what it actually does. So let's just go ahead and execute this. Right, so here we get this select statement, as you can see. I'm just going to copy that out. If we go back to this column and we paste it in, so you can see here that I'm selecting star from the table, and then I have a where clause where I create a big int hash, or I create a hash byte, an MD5 hash from the first three columns. I then convert that to a big int, so I fold it, so I get a numerical value. And then I do an absolute because this hash will be positive and negative, so I want to make sure I only get um, uh, unsigned integers. I want them to be positive. Once this gets through, you can see that I run a modulus on this of 24. So I take the hash, the row hash, and then I run a modulus of 24. So I get a number between 0 and 23. And then I pass in my partition. You can see here this part ID, right? So these are the two variables that got slotted into this code. That and that, right? And if we execute this, I'll just do a top. This might be a bit slow because it's top clause as well. So if we execute, oh, there we go. It was quite fast actually. If we execute that, we get then 100 rows um, of this partition. At the same time, if we were to say 2, we get and let's just look at the first row. We'll get another value in these first 3. Right, so we go ahead and we execute that. You can see here, it's a different value. Okay, cool. So that's what the second dynamic code does. Now, effectively, if we then go back and look at the how this actually gets executed or what the actual result is. If we go back to monitor, let's see, this should be completed. Yep. So you can see again, completed in 8 minutes and 7 seconds. And this, all it did was just copy, and you can see it copied all 24 or ran all 24 in parallel. As I said, the net effect is that you're getting slower throughput whilst doing this. However, um, slower, 6 times slower throughput at, at parallel in 24 executions is a lot faster than, 6 times faster throughput in single-threaded execution. So that's how we, or a very simple way of generating or extracting the data from a source into a data lake. So if we then we're going to go and have a look at the results. There will be some duplication in this because I've obviously ran this a couple of times without cleaning anything out. But as you can see, you're now getting, so if we go here, so step into this. So we're writing it out into a folder where the schema and the table name is, and we can run selects on top of this and get some data back. It's obviously there's this is single file. If we run a count on this, so if we just do a count 1 and execute, we should on this file we should have 1.5 million. Yep, you can see that rounded up nicely. If we select on the entire folder, so that this will be not 37 million. This should be a lot more data. So if we just go and wildcard that and run this query, mind you, it might take, there we go. So I've run it a couple of times, so that, yeah, it's, well, twice. So it's the 37 million times 2. Right. So anyway, that is all I want to go through today. I will link to all the source code and the Git repo where all of this is stored um, in the end description of the video. Right, you guys have a good day. Cheers, bye.